All right, so here we go. So in Calc 1, whether you knew it or not, you investigated two primary problems in the subject of calculus. The first was, you know how much of a quantity you have at every moment, and you want to know how fast the quantity is changing at every moment. That was one problem that calculus addresses. And the second problem is, it's kind of the reverse. You know how fast a quantity is changing at every moment, and you want to know how much of it you have at every moment. So, these are the two primary problems in calculus. In Calc 2, we'll explore both of these, but more of it is endeavor number 2. Okay, a lot of calculus 2 is looking at, you know how fast a quantity is changing every moment, and you want to know how much of it you have at every moment. And what do we mean by a quantity? What do you mean by a quantity? So quantities are like measurable attributes of things like temperature, speed, distance, displacement, force. Okay? Real world quantities are things that you can measure, right? So they're like attributes, characteristics about something that you can measure. So that's what we mean by a quantity. And so we're going to, like I said, looking at endeavor number 2. So what I want to do in this first week or so is kind of do a crash course review of this. You know how fast the quantities change every moment, and you want to know how much of it you have every moment. Since we'll be looking at that problem throughout the semester, let's kind of build it from the ground up, kind of as a crash course review. So I have we're going to review that, and I have a set of principles that kind of build this from the ground up. You know how fast the quantity is changing every moment. You want to know how much of it you have at every moment. And so the principle 0, or like an introductory principle, is this idea that variables vary. Variables vary. So if I showed you this equation, 2x minus 7 equals 0, what do you think when you see that? What do you think when you see 2x minus 7 equals 0? What comes to mind? Does solving the equation come to mind? Does that come to mind? Does x equals 3.5 come to mind? Because that's what you would get if you solved that equation. Okay? So x equals 3.5. What about this? Could x be 4 or 10 or say negative 0.5? Could it be those things? It could? Why? What's that? It can be changing. Okay. So if 2x minus 7 equals 0, how could x be 4 or 10? So the idea is that x could be 4, it's just that what would happen? It'd be wrong, right? The equation wouldn't be true. So that's the way we want to think about an equation like this, is that x could be like a variable. So for instance, suppose x is defined as the number of hours elapsed since your plane left the ground. Okay, could x be 4 if you have a long flight? Could x be 10 if you had a really long flight? Yeah? But even if you had a short flight, could x be 10? The number of hours since your plane left the ground? Sure, it'd be 10 hours after your plane left the ground, even if you made it home or something like that, right? What about negative 0.5? Could x be negative 0.5? And what would that mean? Yeah, like at 30 minutes or half an hour before you left the ground, that would be that point in time. Okay, so we want to think of x as varying, right? So x takes on, it's 30 minutes before, and it's a minute before, and then it's 0, so we're taking off, and then x is 1 hour or 1.2 hours, and so x is as this thing happens, as this story of your plane getting ready and taking off, x is continually varying, right, with time, right? It's the number, and it's taking on the value of the number of hours since your plane took off. And then maybe 2x minus 7 is like this equation that tells you when you get your peanuts or when you get your drink, okay? So it helps you find a particular value of x of interest. But we don't want to think of x as like, oh, if 2x minus 7, then x has to be this 3.5, right? No, it's just that x can vary, and then certain equations will like pinpoint special values of x for us, okay? All right, so in this case, so x takes on many values, many real number. Okay, so what would the variable dx, so that should look familiar from Calc 1. What would dx represent? Oh, no. So dx is a variation in the number of hours elapsed. Okay? So x is the number of hours since your plane took off, and then dx would be like a variation in that number of hours. So for instance, if dx was 3.5, what would that mean? So for instance, if x was 1, and then it took on all the values from 1 to 4.5 hours, right? So x starting from 1 hour since the plane took off to 4.5 hours since the plane took off. What was the variation in x? How much did x change or vary? 3.5, right? So that's what dx would be. It'd be like a change. So notice that doesn't necessarily have a fixed starting point. So x could be 0.72. What would that be? 4.2. Would also represent a dx of 3.5 hours, or a variation, or an amount of change that x was undergone by x. Okay? So super important that dx should look familiar from Calc 1. Super important that given some variable x, then dx represents a variation in whatever the quantity x is. Okay, so principle 1. So principle 0, variables vary. Okay? Variables take on many values as some situation unfolds, right? As some situation unfolds, that variable takes on many values. So rate of change. So we're gonna buy trail mix that costs $3.20 per pound. And so we're gonna put some mix in our bag, but then we decide, oh, I want some more. So what additional cost will you pay for 1.5 more pounds of trail mix? Everyone figure it out, okay? So figure out how much additional amount will you pay if you put 1.5 more pounds of trail mix into your bag. Everyone figure it out. Okay, so put that on hold for a second. So when you have a situation like this, you have a real world situation, a really important thing in this class is we want to model it with mathematics, right? So modeling with mathematics means assigning symbols to the important quantities in the problem. So here is a set of symbols, x, y, dx, dy, and m. Okay, and so we want to assign meanings to these symbols so that we're modeling the problem. And you always want to do this, okay? So you always want to do this when we come to a real-world situation. Okay, what are the variables we want to use and their meanings? Okay, and so I'll tell you that x, I'll give you this one. X is the total number of pounds of mix in the bag. And that's an example of what I'm asking you to do for these other ones. What does y represent? Dx, dy, m. Okay, so I want you to write out phrases like this. Complete specific phrases that describe what these other symbols mean in this situation. And then, task 2, determine if the value of those is known or unknown in this situation. So, x or y, known or unknown. So x, y, dx dy m, known or unknown. Okay, so if you're good to go, you can work on it by yourself. If you need help, you could introduce yourself to the person next to you, ask them, ask one of our TAs. They'll be wandering around. I'm going to start attendance, but this is your task. So 2 things: assigning meanings, phrases to these 4 symbols, and then deciding whether each of those is known or unknown according to the given information. Go. What did you say Y was, Jordan? The additional cost? That's what Y is? Okay, what do you guys think? So that actually what you said is something, but it's not Y. What is the additional cost? That would be dy, right? So yeah, that was good. You said on the wrong one. Y then is total cost of whatever X pounds of the mix is. So then what would dx be? Variation or change in pounds. Okay, so I said a variation in the number of pounds. Dy is what Jordan said. A variation in the cost. And what is M? Okay, our price per pound. Okay, and we call that's the constant rate of change, right? So in this situation, we have a constant rate of change, and that amount is 320. Okay, so known or unknown? The total number of pounds of mix in the bag, known or unknown? In terms of what the information I gave you. Known? The total number of pounds is unknown, right? Because I put some in, and then I added some more. I never told you how much I gave you initially. We added 1.5, so the total number is unknown. What about the total cost? Unknown, okay? What about the variation in the number of pounds? Known? And what is it? So right now, dx is, for this situation, 1.5 pounds. Okay? dy, known or unknown? All right, let's come back to that. M, constant rate of change, known or unknown? Known, okay? So I'm writing it right there, 3.2. Okay, so I asked you to find what additional cost you would pay for 1.5 more pounds of trail mix. I asked you to calculate that. And what did you get when you calculated that? You should have gotten 480. Did you get 480? Okay. And what calculation did you do to find that was 480? What'd you do? What I'm about to do is one of the most important things of the whole semester. So hopefully that gets your attention. How did you calculate the 480? Right, so you're going to take the, did you take the 3.2 and did you multiply it by the 1.5? So what I want you to do is I want you to take that equation and rewrite that equation by modeling it with these symbols. So how would you use these symbols to rewrite this calculation you did to solve this question of how much more would it cost for 1.5 more pounds? So how would you use these symbols to rewrite this equation? Okay, so I know I've got a couple Gabes. Where's one of my Gabes? Gabe, this one right here. Can you do that? So how would you could you rewrite this equation right here using these symbols? M, so this is my constant rate of change, times the variation in my pounds gives me variation in cost. Agree with that? Okay, so this is, and I'm just going to change the order here. I'm going to say dy equals m dx. Okay? So given that change in pounds, the 1.5 pounds, you multiply it by how much per pound, and you get how much more cost, how much your cost goes up. Okay? This right here is the way that we understand the value of m. dy equals m dx is the way in which we understand the value of m. And we say that given any change, so doesn't this tell us, doesn't this value of m, 3.2, tell us that given any change in the number of pounds, it will determine what the change in cost would be. So, for instance, if I change the pounds in my bag by 10, how much will my cost go up? $32, right? If I change my pounds by a half a pound, if I increase by a half a pound, how much will my cost go up? 160. And you get these numbers, you get those values by multiplying by that constant rate of change. So given any change in the number of pounds, that's my dx, multiplying it by the constant rate will give me the corresponding change in cost. I'm going to ask this question throughout the semester. We're going to have a constant rate of change. So I'm going to say, tell me what the meaning of the constant rate of change is. And the meaning is this. Given any change in whatever x means, your change in whatever y means is going to be that constant rate times that change in x. Super important. And it may take us about 3/4 of the semester to finally get it. Because in a couple weeks, I'm going to ask you that question, and you're all going to go, I don't know. So try to remember, learn this. This is how we frame the meaning of the constant rate of change, $3.2 per pound. That given any change in the number of pounds, it determines, that constant rate determines what the change in the cost is by multiplying those together. Okay, and this really is kind of the core, the heartbeat of this. And this is what we're all about this first week and the whole course. You know how fast the quantity is changing at every moment. You want to know how much of it you have. So you know how fast the quantity is changing at every moment. Where is that found in this equation? M, right? We know how fast the cost is changing per pound. And we want to know what? We want to know cost or increase in cost. So given that you know how fast the quantity is changing every moment, dy is going to help us build up how much of it we have. Little changes in cost come together to let us know how much our total cost is. So this dy equals m dx is the core principle of this endeavor that we're kind of building up here, unfolding. You know how fast the quantity is changing at every moment. That's m. You want to know how much of it you have. We can easily figure that out with dy's, right? With changes in cost, we can figure out what our total cost is. Does it make sense? Super important. Watch that part of the video again. All right, let's go on to another example of principle 1. All right, so now we're going to remove 0.4 pounds from the bag and return it to the bin when no one's looking, right? So same thing, now new situation. Tell me, so x and y have the same meanings? They actually all have the same meanings. Do we know what dx is in this case now? What would dx, is it known or unknown? The change in number of pounds. And what is its value? We're going to decrease x, so that a decrease gives a negative dx. Do we know what y is? How do we find the change in cost given that change in pounds? How do we find the change in cost given that change in pounds? Yeah. Yeah. Yeah, mdx, right? So that's what I just talked about. Like I said, given any change in pounds, we can figure out the change in cost by doing mdx. So it'll be 3.2 times negative 0.4, and we get 1.28. How can you have a negative cost? It's not really a negative cost. It's a negative variation in cost, right? dy. It's a negative dy, meaning that the cost went down, right? So the cost went down. So a negative variation or change means a decrease in that quantity. Okay, we're decreasing the cost by 1.28. M is still the same. Is it M negative or positive? Still positive. So with a decrease in the pounds, you're going to have a decrease in the cost, according to dy equals m dx. Any questions so far? All right, new example. A soldier lowers an American flag from the top of the pole at 0.75 meters per second. So here's my question that we're going to start talking about. How much does the height vary from 0.6 seconds to 2.4 seconds since the flag left the top of the pole? So we're going to start by doing the same thing. I'm going to tell you, you start by modeling, right? Modeling the mathematical situation with symbols, okay? Those are our variables. So I'm going to tell you that y is defined as the height of the flag in meters. So I'm going to give you that one. And you're going to do the other four. So you're going to do x, dx, dy, and m. So you're going to write out a phrase that's specific and tells the meaning of that symbol, and then whether in this situation, whether the value is known or unknown, just like last time. Everyone's either making progress or getting help. Either making progress or getting help. Find a TA, talk to the person next to you, go. All right, Tyler, you're up. How about x? Did you tell me what your meaning for x was? X is the distance the flag has traveled. What do you think? Distance, is it Oren? Is that right? What do you think x is, Oren? So we have distance that the flag has traveled and distance since the flag left the top of the pole. What do you think? Time since the flag left the top of the pole. In what, seconds? In seconds. Time since the flag left the top of the pole. Okay, what about dx then? James. James Sorbel. Variations in seconds. Some variation in seconds, right? In this situation. From such and such a time to such and such a time. Okay? But then it's that how much it changed, right? How much x varied. Okay? What about dy? So we know y is the height of the flag. What about dy? Phoenix? Variation of the height of the flag. And then what about m? Where's Rebecca? Jernigan.
Here,
yeah.
I said that was for m is the rate of change, and that is listed as I put it as -0.75 meters.
Okay. All right, good. All right, so let's see. We said x is the number of seconds, right? Y is the height of the flag. Dx, change in time in seconds. Change in the flag's height. And m is the constant rate of change. And so is it 0.75 meters per second? She said negative. Should it be negative or positive? Why negative? Why did you say negative?
So I just think that it depends on where you put zero. So if you're thinking of it as lowers and zero, it's not going up because that would be positive. It's going down, so it's negative.
Right. So y is defined as height. That's up from the ground, right? So zero's at the ground. That means y increases as you go up. So this flag is coming down at 0.75 meters per second, which means m has to be negative 0.75, right? Because y is changing, y is decreasing, right? Y is decreasing according to how y is defined, the frame of reference for y, which is pointing upwards, height. Okay, so is the number of seconds known? Known or unknown? Number of seconds. X, values of x. Known or unknown? What about 0.6? Is that a value of x? Yeah, so often we'll do like this. We'll say x initial. So x sub I, 0.6. And then 2.4, is that a value of x? And we could say xf, like x final. So those are two values of x that are important, but what about just x in this situation? What about just x? How could we talk about what x means? If it starts at 0.6 and ends at 2.4, then what value does x take on? Not the variation, that's dx. It could, yeah, it could be the final, it could be the initial, it also could be, what's that? All of them in between, good. Variables vary. X takes on every value from 0.6 to 0.24, 0.7, 0.75, 0.8, 0.81, 0.82, 0.9, 1.0, 1.5. So X is varying as this is happening, right? So X takes on every value in between. So it takes on all values from 0.6 to 2.4 seconds. All right? What about the height of the flag? Known or unknown? Unknown. We don't know where it started, right? Okay. What about change in time? The change in time in seconds in this situation, do we know it? What is it? Someone said it. 1.8, right? It's how much time varied starting from our initial time to our final time. So dx in this situation would be 1.8. What about dy? How can we know how much the height is varied? Right, so what do we know? Given a constant rate of change, given any change in x, we know what the change in y is, right? So our constant rate of change, negative 0.75. That's how much it's going down per second, and we have a change of time of 1.8 seconds. That's our dx. So times that constant rate will give us, what, anyone find it? What is it? Negative what? 1.35. Thank you. Meters. So the flag, so the dy for this particular situation is 1.35 meters that the flag came down. Okay, questions on this slide? Okay, we got to move. We got 4 minutes to do principle 2. Any questions? Here we go. Stay with me. Now I want, how much does the height vary from 0.6 seconds to x seconds? Now I'm going to truly let x vary starting from 0.6 seconds. And I want to know how much variation in height do we get from 0.6 to any number of seconds x. Okay, what's dx now? Right, it's the variation from 0.6 to x. So dx would equal x minus 0.6, right? There's our variation height, our constant rate. Our variation in the number of seconds is x minus 0.6. Given any value of x, we can subtract 0.6, and that will be the current variation dx. So really what we're asking here is we're no longer asking for a particular value of a change in height, but any value of change in height. So this is what we call a net accumulation function. So given values of x, we get different values of dy. Right? So depending on what the values of x is, I get a different value of dy every time. That's a function. That's what a function is. All right, so what would it be? So dy then we can write, well, this is what's called function notation. That's another way, in this case, of saying dy, and that's saying for any value of x, this whole thing that I put a box around is the change in height of the flag. And that's calculated by our m times our dx, which is x minus 0.6. Okay, so function, you're going to be reviewing function notation in recitation this week. Super important in this course. So make sure you're 100% there, and then you'll have you'll have an assignment due Friday on function notation. Okay, so this is our net accumulation function. Quickly here, still a couple minutes. So again, m dx, but now dx is a function of x, so then dy is this function of x. All right, so this is principle 2, a net accumulation function. So same situation. I'm going to show some graphs here. We're going to sketch the rate of change function, and we're going to sketch the net accumulation function. So for both these functions, the independent variable, or the thing on the horizontal axis, is our time since the flag was lowered. So that's number of seconds. It's the same variable x on the horizontal axis. What will the rate of change function look like? What will the rate of change function look like? So given values of x, what is the rate of change? Yeah. Okay. So all lines are straight. What you mean is what? Horizontal, right? For every value of x, so here's our rate of change. For every value of x, the rate of change is negative 0.75. Is that what you were thinking? Okay. So that's the rate of change function. No matter how much time has gone by, you always get negative 0.75 as the rate of change. And so that's represented, these are all points, right? So this is a point, this is a point, this is a point. And each of these points tell us that for that value of x, the rate of change is that same value, negative 0.75. Okay, now the harder one is this net accumulation function. The net accumulation function, right? So that's how much change, the net change in height since 0.6 seconds, right? Starting from 0.6 seconds. So at 0.6 seconds, how much change in height have we had since 0.6 seconds? 0. So what point would that give us? 0.6 and? So that's going to start here. This net accumulation function is going to start at this point, 0.6, 0. Because there's been no change in height since 0.6 seconds. And then what's this function going to do? What's it going to look like? Draw it with your finger. So I saw this. Is it going to do up, exhibit A, or down, exhibit B? Changes in height will be negative, right? Because our rate of change is negative. So this net accumulation function will look like that. That's the negative 0.75 times the x minus 0.6. Given any value of x, this tells you what the corresponding change in height was since 0.6 seconds. So here's 1.4. So this y value tells us how much the flag has gone down at 1.4 seconds, starting from 0.6 seconds. Okay, so you got the short worksheet. Will be released soon on Canvas, and you're filling that out, posting it back to Canvas by 9 a.m. Wednesday.